that I have a chance to be able to do this again. Today we'll be talking about a brief history of memory leaks. Um, I have given this talk before, but it has been revamped quite a bit since programming Android with Kotlin has come out. This is a book that I co-authored on Android and Kotlin, and yeah, so without further ado, we'll get going. All right, so if you're unfamiliar to Chicago Kotlin user group, we believe in being inclusive. So Chicago Kotlin user group is an inclusive group. It means be curious, ask questions, and avoid assumptions. And even in pandemic, always do everything to continue to grow trust, empathy, and friendship. Oh, going too fast today, you know. I have those extra nerves just because I'm giving that talk today. So are you interested in giving a talk? We do have an open CFP year round. It is open to both experienced and first-time speakers alike. We've had probably about half and half, and it's all been just wonderful talks. So please feel free to use us for practice, especially if you have other upcoming talks or maybe you have some side projects that you'd like to share. It's a great way to expand your network. It's a safe space to practice talks, and it looks great on a resume. Oh, and if you'd like to get connected with the Chicago Kotlin user group, we do have a Slack channel in the Kotlin Lane Slack. It's in the Chicago Slack channel, and you can also follow the Chicago Kotlin user group on Twitter at Chicago Kotlin. Okay, so for live reactions and interactions, it's a little unfortunate it's underlined, but we can use the YouTube chat. I'll be doing my best to keep an eye on it. And we also have the Twitter for Chicago Kotlin and also MVNDY_HD. That's like my Twitter name if anyone's interested in tweeting at that. Okay, so you know, without further ado, you know, there's no transition needed. So I guess I can just go ahead and switch over into this talk. I am, just give me a sec. All right. Thanks to everyone for being patient. And I hope folks don't mind. I do have two parakeets. They're just going to be in the background. They're usually good unless it's really important and it counts. So there's always a chance that they could act awry. Yeah, so welcome everyone to a brief history of memory leaks. There we go, we're getting settled in now. All right, so for those of you that may not be familiar, I had co-authored a book called Programming Android with Kotlin, Achieving Structured Concurrency with Coroutines. It is an O'Reilly publication, and the goal of the book is to provide a solid foundation on Android fundamentals to ensure proper practices with structured concurrency, and to show readers how Kotlin has evolved Android development by giving the historical context needed to be able to fully appreciate the problems Kotlin solves in Android. So yeah, this was a really fun book to write. I came in at a later time. The two original writers were Pierre and Lawrence, and unfortunately, Pierre and Mike Dunn. Unfortunately, Mike had passed, and I had joined on, and Blake joined on a little bit later. Yeah, but it's been a really, really fun experience. I would say that this book, there's a lot on Kotlin and Android. It's intended and beneficial for pretty much any Android developer, whether you're going from Kotlin to Java to Kotlin in Android development. And there's a lot of, we kind of wrote this book with a few goals in mind, one of them being, sometimes the only way to have an upbringing in Android is to make mistakes. And we hope to capture some of those mistakes in this book. So there's just a lot rolled into this. That being said, we're at an exciting point in history, watching how Android and Kotlin has evolved together ever since Kotlin has been adopted as the official language for Android by Google back in 2017. So yeah, this talk will be looking at a particular case. We could kind of consider it sort of like a Freakonomics story, if that. But the case is memory leaks in Android development. Yeah, so when the Kotlin team made coroutines, they had this desire to create thread-bound UI programming for Kotlin coroutines. So when coroutines were designed, there is a sort of mindset that Kotlin doesn't have any standard APIs to work with resources and doesn't define any resources in its common standard library. So all the resource working API are for JVM only and are based on the JVM resource management designs. So you'll see here that we have a timeline with just like a couple of years. So we have 2017, 2018, and 2019. When we started looking into memory leaks, there isn't too much out there on it for Android development. Sure, there's like a lot of like beginner topics, but I thought it might be helpful to kind of just like describe like where we come from and where we're at. Yeah, so just starting with 2017, when JetBrains officially came out with coroutines, they described coroutines like lightweight threads. Roughly a year later, Roman Elizarov, in his talk called Coroutines in Practice, kind of came back and said, wait, coroutines, like you can't just spin off as many as you can. There actually is a cost to it, depending on what resources are being consumed by those coroutines. And a year later, in 2019, another talk came out for structured concurrency, addressing like some of these items, which we do talk a little bit about later in the talk. Okay, so I kind of like mentioned this story, and it's just kind of like, okay, so how did we get from, okay, coroutines are like lightweight threads. You can spin off as many as you want. And then a year later, we're saying, okay, wait, actually there is a cost. Well, the short answer to that is, sometimes using coroutines, especially in other systems like Android, it can be easy to end up like creating memory leaks. So I started asking myself, memory leaks, it's something we don't talk about too much. What's the furthest back evidence of memory leaks? Does Android start really talking about it? So there actually is a really, really great video blog on YouTube called Performance Matters, and it's for Android developers. It talks about performance problems with Android, and they do an excellent job covering like an introduction to memory leaks. But the earliest I can find is an Android developer blog called Avoiding Memory Leaks back in 2009, but not too much since then. So kind of laid low until 2016 or so. And then they started really popping back up, as Android started growing in maturity and as Kotlin coroutines started coming into play here. So actually, it's really interesting because memory leaks can occur anywhere. It doesn't have to occur in just Kotlin. It doesn't have to occur in just Android. yeah, it can happen anywhere. So, just some other like fun things that I found, there, even in 2016, so this is, a year before we're saying that coroutines are ready to use, they're lightweight threads. There was like a reported memory leak for coroutines. This was fixed now, but initially, the challenge about memory leaks is that uh, the definition tends to actually this kind of brings us to our conclusion here, which is that memory leaks, they're just everywhere, and they're in our apps, they're in the IDEs, they're in your phones. We're going to keep creating them, and we're going to keep finding new ones and fixing them. So just like before, where memory leaks tend to pop up, and then later on we realize they're memory leaks and we fix them. They can be sneaky. So with that being said, um, for those who might be wondering, what is a memory leak? Well, a memory leak, at its simplest definition and perhaps its strictest, is when the heap holds to allocated memory longer than necessary, or when an object is allocated in memory but it's unreachable for the running program. The relationship between memory consumption and power consumption in Android is symbiotic. So we care about memory leaks because the more memory is freed from allocation, the more power it requires from the device. So if a device is low on memory, battery drainage can become a concern. And it also affects the ability to kill and quickly resume applications. So uh, yeah, okay. So we talked about kind of like what that brief definition of memory leaks are. I put in actually like kind of some more specific examples around what that might mean, at least for Android. So it's possible, and not just Android, but just general Kotlin. So it's possible to leak references, for example, if you're not careful with the scheduled work and concurrency that you might be writing. And then for when an object's allocated, but then it becomes unreachable, a good example of that is passing some kind of Android component outside of main threading. We're going to cover that in much greater detail later. So yeah, again, feel free to ask questions in the chat. I'll do my best to keep an eye on it and try to answer throughout the talk. But yeah, we'll just go ahead and continue on. So another thing to be aware of with memory leaks is that, like I said, they can be found anywhere. They can be found in your own code. It's pretty easy to write memory leaks in your own code. It's also possible to find it in third-party libraries and even the OS itself. Okay, why do memory leaks matter? Earlier we talked about how serious memory leaks can lead to some serious drainage, but it can lead to dropped frames, jank, whatever, other strange behaviors, and all this ultimately affects the user experience for the application. So, unfortunately, unlike iOS, Android does have limited resources and hardware capacity. So roughly 15% of Android users use Lollipop and below on their devices. That is lower memory. So if you do have memory leaks in your application, your users are more likely to experience crashes, especially with those lower memory devices. So it's about making your application more usable and more accessible to a wider audience. Yeah. So, yeah, it's your responsibility to do everything you can to manage those processes and minimize that power and memory consumption. Okay. So at this point, earlier in the when we're talking about memory leaks, we kind of talked about this heap, which holds this allocated memory. So you might be wondering what heap is. Um, well, we're going to talk about heap and garbage collection. So in Android, every application has its own process and Heap. One of the beautiful things about Android development is that it's self-managed memory heap and the garbage collection mechanism it uses is responsible for freeing allocated memory back to the heap. This is, unlike using, the older version of like iOS development where you're responsible for allocating and deallocating all the memory yourself. So it's something that we don't have to worry about too much. However, there is it is possible for overhead to occur when objects are created and destroyed. So yeah, JAG can occur if one is not careful with the kind of objects that a device holds in the heap from repeated garbage collection that might be unable to clear out references. Yeah, so the garbage collection itself, the mechanism will find data objects in a program which can't be reached in the future, and it reclaims those sources by freeing those objects. So any objects that might be available for garbage collection would be any nullified object references, um, any object references that have been reassigned, and objects that have been created within the method that'll be destroyed once the method fully executes. So anytime the garbage collection mechanism searches through the heap and it's unable to destroy things or unable to correctly identify, hey, this is not being used anymore, that is a memory leak because we just continue to hold it even though we don't actually need it. Okay, so you can actually get two different kinds of memory leaks, implicit memory leaks and explicit memory leaks. Yeah, so to talk a little bit more about explicit memory leaks, I wanted to touch on the Android threading system. So some of the characteristics of the Android threading system might surprise you. Consider the following scenario where a user clicks a button in the application. When it starts and the service also starts running, the thread system will not create a separate thread and will just have all the components run on the main thread. So it's your responsibility to offload longer running work to a background thread and okay, apologies for that. There were some technical difficulties there. I'm going to go ahead and pop that screen back on and we'll just continue right on. Thanks for your patience. Okay. Right. We were talking about the Android, the Android, the UI thread, and also how some of the characteristics of the Android threading system. Right. So some rules about the Android threading system. The Android system has a main thread or a UI thread, and there's also a ton of background threads. Your Android UI components, the view components in particular, your UI widgets, all of that stuff is expected to live in the main thread. So the main thread is responsible for interacting with those views. The main thread allows Android components in the application to interact with the Android OS, like the service the service, the started service that I was talking about as an example earlier. And also, all components run within the same process, instantiates on the UI thread. And storing references to Android components in background thread can cause leaks, so do not do that. The rule is keep your views, fragments, activities, contexts, that all needs to stay within the main thread. Okay, so here is an example of an explicit leak in Android in particular. So for non-Android folk, any context activity fragment view that is an Android component, it is something that has a life cycle, which is why we discourage holding any permanent references, since these life cycles are kind of out of our control and does make the life of these particular items very unpredictable. So the philosophy is to just, if you're able to just kind of keep your interactions with those components, your Android context, activity, fragment, view, if you're able to just keep it in the UI thread, just keep it there. So never store a context or any other Android component into a companion object. A static object lives forever. It's going to stay there. So, you know, that's an easy explicit memory leak that can be fixed. That's the nice thing about explicit memory leaks. They can be kind of easy to detect by eye in the code. So it's something you can see in code reviews. You also want to avoid injecting these very same Android components into background threads. Yeah, for very similar reasons. Okay, so we have explicit memory leaks. We also have implicit memory leaks. It's also possible to accidentally cause an implicit memory leak, meaning that other code behind the scenes might cause one. So yeah, these are a little bit harder to spot off the bat, and it can be located in your own code, but it's also important to be wary of third-party libraries that may reference the use of Android sources. But of course, this is true for any platform, to just be aware of what memory leaks might be present. Actually, this kind of brings us back to our fun timeline. So until AsyncTask had been deprecated in late 2019, it was the most commonly used Android primitive to send a task to a background thread. Despite its good intentions to enable easy multitasking in Android, its most common uses for integrating results back into the UI often ended up causing memory leaks, missed callbacks, and other unpredictable behaviors. So unfortunately, that is not shown in this slide, but yeah, kind of the same year that Structured Concurrency came out, Android had also deprecated AsyncTask. So going into AsyncTask, you'll see here that we have a main activity, which is holding some async task, which extends the class AsyncTask, and it does whatever. The issue with this is that an inner class extending this async task is sitting within an activity or fragment, and it holds an implicit reference to the enclosing class until the object is destroyed. So if the main activity is destroyed, an implicit reference could be held in some async task should the threads still be running, even though that activity is dead, meaning that the heap would end up holding a reference to that main activity, so you end up getting that memory leak. Okay, so we talked about being wary of third-party libraries. I thought this one might be an interesting one to share. Yeah, so memory leaks that are permanent are obviously really bad. However, the definition of memory leaks for those that are most conservative is when a reference is simply held longer than necessary. So this, I'm bringing in kind of an interesting one from the Android OS perspective. Yeah, so there's an issue where the fragment's view, but not the fragment itself, is destroyed when a fragment is put on the backstack. This was an issue that had been registered in Issue Tracker for Google, and it's under the issue called Memory Leak with Nested Fragments and Data Binding. The response from the folks working on Android explained that even though it's not in documentation, developers are expected to clear refs for views in the call fragment on destroy view. Yeah, so not clearing view references in the fragments on destroy view causes these views to be retained using the backstack, and this may not be ideal for smaller. This may not be a bigger deal for small applications necessarily, but for large applications, this can end up accumulating quite a bit and having a bit of a disastrous effect. Yeah, so here is a Twitter reference regarding this particular issue. Yeah, so I'll just read it. It's a tweet from PY, and it says, "This answer is 100% wrong, and I'm sad that this is the answer given to a developer trying to fix leaks. If you add a fragment to a backstack, you better clean up all view references in fragment.onDestroyView." And he links a definition in his library leak Canary, which we will talk about shortly. And he also links the issue tracker with a screenshot of the resolution for the ticket, where it says status won't fix intended behavior. The fragment's view, but not the fragment itself, is destroyed when a fragment is put on the backstack that is working as intended. Leak Canary requires that you null out all references to views when onDestroyView is called. While this is technically not a leak, the reference will eventually be cleaned up when the fragment is permanently destroyed, and Leak Canary has chosen to treat it as such. So in this case, this is a memory leak, which technically gets cleaned up, but there are some arguments as to what that definition is. Personally, my co-authors and I, we kind of err on the side of treating this as a memory leak. So, of course, memory leaks can be a bit subjective, but use your best judgment. Okay, so just some quick review. When the heap holds to allocated memory longer than necessary, that is when you have a memory leak. You have two different kinds of memory leaks. You have explicit memory leaks and you have implicit memory leaks. But there is another yet infamous kind of implicit leak, and I think it's captured perfectly in Roman's tweet. He says, "There are three categories of programming bug complexity: simple bugs, hard bugs, and concurrent bugs." So imagine that you're developing an application to help users plot, plan, track, draw, and share information about hiking. Your users should be able to navigate to any of the hikes they've already completed or are in progress. So if you were to make such a call, it is likely that you'll be having different data sources to draw from. So just so folks know, if you look at your YouTube chat, I did post a link of the TrekMe GitHub repo. If anyone is interested, that is an open source library, which is a lot of fun to look at, and it's also used extensively for examples in the programming Kotlin with the programming Android with Kotlin book. Okay, so some things about this problem. Let's say that we try to address this with regular Android threading. You have some drawbacks here. Callbacks can rapidly become complex and hard to maintain without thoughtful design. You must account for listening to lifecycle events. And with threads, you have to require a thread-safe way to interrupt threads. Yeah, so let's say that, we're going to go back to that problem that we were talking about. We have different sources to fetch from. So this can be a little bit heavy You might be interested in running parallel processes at once. You won't be able to do that with a single thread. One possible option is to kind of create like a thread pool executor, which is just a primitive that can be used. Yeah, so in situations where a background task might take a long time to execute, you'll probably need more than one background thread. Yeah, so this is a thread pool executor. It's a primitive that lets you spin up a number of threads and toss it into blocks of work for execution. So there's also some kind of like difficulties around this as well. I do want to point out that Android devices, and as it's true for any physical device, but you don't necessarily want to have too many threads because CPUs can only execute a certain number of threads in parallel at a time. Okay, so going to an implementation example using threads, and this is done in a thread-safe way. So this actually addresses a lot of potential issues. So this is just kind of like, here's an ideal scenario. So fetch hikes for users and fetch weathers function should be invoked from a background thread. And in Android, you can do this a number of ways. Java has the traditional thread library, of course, and then there's the executors framework, which we discussed briefly. The Android, for those of you that don't use the Android, there's also the standard Android library, which has the now deprecated AsyncTask handler thread, as well as a thread pool executor class. So looking at the code, we have a view model, which is just kind of like the presenter logic. You have an executor service, which kind of holds the IO thread pool. And there's kind of like just, you have some concepts of thread safety within this particular piece of code already. So that is a good thing. So it is thread safe since the mutable state for the data is being held only kind of like in one thread instead of being placed in a bunch of threads, because then you can end up with some serious issues around concurrent modification there. So you do have that aspect. Also, in this case, we have the executor service, which kind of gives you a handler, a runnable, which holds like a handler. So you're going to spin off a handler every time. And the IO thread pool is responsible for sending those calculations to the background thread. And once we're within the block for the runnable, that stuff is back in the main thread. So we've run off and we got the networking or the data's, data store, whatever, off in the background thread, and we posted everything once we received the results. Okay. Apologies. Of course, there's internet issues. So one day there's a KUG meet. That's always how that works. We're gonna pop right back in. All right. Yeah, so we're talking about traditional thread safe methods in Android. We're talking about how there is some sense of like thread confinement. Also, the threading is just kind of like carefully handled. So this is all great. What about memory leaks? So we've actually addressed a lot of those potential memory leaks, as I've mentioned briefly. We talked about mutable data. Thread confinement prevents this. Having the mutable state live in only one thread, which can produce, otherwise it having that mutable state live in more than one thread can produce leaks and thread exceptions. Yeah, making sure that the runnable handler is not accidentally left open, setting up the correct thread, setting up correct threading. So we talked about all that. So this is all fine and good, but I think this already poses some problems, which is just kind of the simple fact that it's like a lot of effort and maintenance and care and that you have to put into traditional thought and design into being able to offload tasks through traditional threading methods. So, you know, that is like kind of like one pain about these kinds of implementations. We also have one misconsideration for memory leaks, which is thread cancellation. Yeah, that stuff can get super ugly. So in situations where a background task, you know, like let's say that we have some threads running and one of them breaks, we have like a network call that fails or there's some parsing issue. The work isn't going to be able to stop. Threads are cancelable, but sort of. It's gonna cancel when the work is done. That's really how it works. So it does make execution flow like really hard to control. Yeah, so there's definitely some difficulties around that. And then you have other limitations in Android threading to consider. So in threads, exceptions are not propagated. That's really important because if you end up having a crash in a thread, it becomes really hard to figure out exactly where that issue is coming from. Also, you know, this is something that I feel like can be a debate a lot in the industry. Android designers made the choice to crash the app if there's an unhandled, uncaught exception handler as a choice to make it fail fast. This is great for Android. Maybe not so much for app developers who want to keep customers. A crashing app is not good if you want to keep those customers. Yeah, so anyway, we've talked about a lot of considerations with this kind of you know, fetch hikes call. And the good news is that even though there's a lot of difficulties and pitfalls with the traditional Android threading, there is a cancellation mechanism that's much easier to work with in Kotlin coroutines. And there are some extra benefits. So around using Kotlin coroutines, for example, Kotlin coroutines does not require data primitives like handlers to pass data. So that already takes out one job that we would have had to worry about otherwise. And it is possible for coroutines to be made with safe cancellation mechanisms, and it is encouraged if you use it in a very specific way. So we're going to revisit this on hikes fetched with coroutines. We're going to pretend like we have access to the code, and we're going to just redraw the situation again. So this is, we have the fetch for hikes, and maybe we're getting winds, maybe we're getting temperature data, maybe we're getting hike data. It's coming from different sources. And in this case, we start off with some parent coroutine, which spins off some child threads. That is the benefit of using coroutines versus traditional threading. With threadings, you can't create child threads, but in coroutines, you can create child coroutines. So yeah, if a crash is thrown, all the coroutines would still be there. So normally we catch this exception at the top and try again, but then we spin up another set of coroutines, the same thing happens, and the remaining coroutines are still running. So even though these coroutines are smaller, I mean, we do this so many times, and this does like accumulate as well. So this is why we want to be able to implement coroutines that are able to automatically cancel dangling background threads to reduce the risk of memory leak. So there are different kinds of exceptions to consider, you know, at least, you know, in client code. So there's exposed exceptions. So these are the only kinds of exceptions which can be handled by the client code within a try-catch. And then there's unhandled exceptions, and those are the ones that are really hard to account for. These typically make your application crash, or at least recovering from them might leave the app in an undetermined state. So luckily, Coroutines offers an option to be able to capture these kinds of exceptions. So if all else fails, you can register a custom coroutine exception handler, and this is how you're able to capture these unhandled exceptions. This is also short for CEH, so I'm just going to say that probably for the rest of the time. So if all else fails, your last chance to handle an exception is to register it as a CSH. This stops exceptions propagation from getting swallowed, and it avoids program crashes. A coroutine exception handler is conceptually very similar to a thread uncaught exception handler, except it's intended for coroutines. It's a context element, which should be added to the context of a scope or a coroutine. And the scope should create its own job instance, as a CEH only takes effect when installed at the top of a coroutine hierarchy. So registering a custom handler also gives you the benefit of printing that error that you registered also into the stack trace, because before you would get something really, really big, just uncaught exception and no stack trace, nothing. So this is a huge deal. Okay, so to be able to register a CEH, you must have the following components. The launch must be a coroutine root builder, and there must be a scope and a supervisor scope to register the child to. Yeah, so now if this crashes, the exception is going to be caught by the scope, and the scope cancels all the child coroutines. So this parent scope will monitor all the child scopes that have spun off. So the coroutine scope expresses uncaught exceptions, but also notifies its parent and then waits for the launch completion before the cleanup, and it doesn't leak jobs. So there's also a regular scope there's a supervisor scope versus a coroutine scope. In this case, we're using a supervisor scope. One crucial difference is that with the coroutine scope, it only propagates cancellation downward and cancels all the children only if it fails itself. So this one works a little bit different. Yeah, also you'll notice the coroutine builder is on that launch. So the two types that you could launch a coroutine with is launch or async. It would not use async because it would expose the uncaught exception, which could then be handled with a try catch. Yeah, so there was a lot of really tough stuff in here. This was kind of a sneak peek at kind of how deep into these issues we get into. Yeah, but I think this is kind of an important concept to learn. There are a lot of other different ways to handle exceptions in your application design. It depends on what the business requirements call for. But I thought this was kind of a good base level to talk about, well, what's the most base thing we could talk about for talking about cancellation and making sure that those items don't leak. So unhandled exceptions using CEH. If all else fails, it's your last chance to be able to catch it so you can register a custom CEH. And if you decide to use it, just make sure you end up using it at the top of your coroutine hierarchy or on the supervisor direct scope. Okay, talked about a lot of stuff. We talked about implicit memory leaks for a really long time. I mean, there's just a lot of different ways it could go. Yeah, catching implicit memory leaks are really hard, but luckily there is an open source library that can help you catch memory leaks easy called Leak Canary. There is a video demo that I do have where I, don't make fun of the Nexus thing. I think I was just really lazy. But you can see in the code that I'm running Android Studio, And I have a Google Maps view fragment opened up, and there's that on destroy view call that we kind of talked about a little bit earlier. Yeah, so I made fetching tiles for loading the map for TrekMe abnormally slow. So I went to create a new map, and then I waited long enough to see if the tiles started to appear, and then I start rotating the device. And you'll see that in the code, I commented out the destroy and the nullify. And Leak Canary ends up catching that memory leak after I've rotated everything. And then you can also see that the profiler is also open. That is another Android tool that is excellent for profiling your application. Would highly recommend using that in tandem with Leak Canary. And for those of you that has never used Leak Canary, some wise words from my co-author is, before you use Leak Canary, make sure everyone on the team is ready for that conversation. So yeah, you can see that Leak Canary is configured, and once it detects those leaks, you can actually look at the stack trace that's given to you. So it is quite nice. But definitely, if you don't use it already, would highly recommend using it, as it's just good practice. Okay, so we're wrapping this up. I understand there was a lot of information here. I have some tips at the end for avoiding potential memory leaks, so be sure to profile your app. Follow the constraints of your Android profile. Think about what components you're using. Avoid persistent services if possible. Be careful, like if you're working with services in general. Just items like that. Pay attention to static references. Don't reference activities, views, contexts, anything like that outside the UI thread. Make use of coin, make use of glide. And there was a lot of information here. But if you're interested in hearing more, the Programming Android with Kotlin is out. I thank everyone for their time and sticking through. Please let me know if what questions you have for me. I'll give a few minutes. And other than that, I think, that's everything for now. Yeah. There was a lot of information. I do appreciate everyone taking the time to look into this. I was excited to talk about some of the items from here. This was my first time kind of doing this, so I'm sure there's a lot of work to be done and things to trim down. So we shall see. But thank you again. Keep an eye out. There are upcoming Chicago Kotlin user group meetups coming up with more Kotlin GDEs. And don't forget, if you'd like to submit a talk yourself, go and check out the description and be sure to submit a CFP. Okay, thank you, everyone. Happy Wednesday, and take care. We'll see you next time.